So this lecture is devoted to deriving what are called the series and parallel combination rules for capacitor networks. So let's do the series first. I introduced in the previous video some rules about how the charge is going to move around, the fact that net charges have to remain zero, and also something about potential differences, right, on between conductors and on the same conductor. And you're going to hear me use those three basic rules in order to derive these formulas. So do you remember that early in the introduction to capacitance, I mentioned that in order to determine the capacitance, you have to explore the capacitance. And this means imagine charge separating, right? So go ahead and separate charge. So I'm going to assert this myself. I'm going to say that capacitor C1, I'm going to imagine removing the charge Q from the right-hand side and putting it on the left, which leaves behind negative Q. But because the net charge of this middle conductor has to remain zero, it's got no choice but to put the other opposite charge on the other side so that the net charge of the middle conductor is zero. And since capacitors always have the same charge on either plate, it's got to be like that. So I first asserted a charge separation on one of the capacitors. Then I conserved charge on the middle capacitor, which leads to a particular charge on the third conductor. All right? So I've got all the charges. But here's something interesting. What's interesting is because of the separated charges, I have potential differences. So the potential difference across capacitor number one is equal to, so I always forget this, so I always have to go down and remind myself that the basic definition of capacitance, it's whatever charge is separated divided by whatever potential difference there is, right? So it's charge per voltage. So if I want to solve for voltage, then I just do a couple of algebra steps, and it's Q over the capacitance, right? So the potential difference across capacitor number one all by itself, because of my asserted charge separation and the value of the capacitance that you could consider a known, is just, so separating the charge Q, and the capacitance of that capacitor is this. This is, you can do the same thing. In general, it will be a different potential difference across the second capacitor, right? Asserted the charge separation being the same, so that's just the same up top, but the capacitance is a different value in general. So remember that the goal is to take our series combination and imagine it as being one capacitor, a single capacitor, whose equivalent capacitance is the thing we're trying to determine. So the equivalent capacitance in this case, right? Let's think a little bit. The total potential difference from here all the way to here, right? So let's call this position 1. This I'm going to say is position 3, or conductor number 3. And this is conductor number 2. So the potential difference across capacitor number 1 is the potential difference between conductor 1 and conductor 2. And the potential difference across capacitor number 2 right? Capacitor number 2 is here. It's in between conductors number 2 and 3, right? So these two potential differences, right? I want this equivalent capacitance, so I imagine the left side being actually the same conductor, and I imagine the right side being the same conductor, and the potential difference across the equivalent capacitance is equal to V1 minus V3. Oops. So V1 minus V3 is the equivalent potential difference across the equivalent capacitance. And this is equal to, so it turns out that V1 minus V3 is just the potential difference across capacitor number 1 plus the potential difference across capacitor number 2. So as a caution, I'd like you to notice that on the one hand, I'm talking about differences in potential that are across capacitors. They are the differences in potential of the potential of one conductor minus or differenced with the potential of another conductor, right? So this can be quite confusing. But if you go in and you just fill in what this is, it's this minus this, and what this is, which is this minus this, what you're going to notice is that when you add this and this together, can you see that the negative V2 and the positive V2 are just going to cancel? And in the end, it'll be V1 minus V3. That's the result of this. So the potential difference across the equivalent capacitance is the sum of the potential differences across the two capacitors in series, right? And this actually is going to be our backbone equation. So the potential difference across the equivalent capacitance is just, right, the charge separated over the capacitor, over the equivalent capacitor, divided by the value of the equivalent capacitance, right? This is just the definition of capacitance. It's the real, and we're associating it with an equivalent capacitance, right? C sub EQ for equivalent. So when you go up here, if I was to separate the charges where the charge capital Q symbol is the separation of charges, this is the charge that sits here, and this is the charge that sits over there. So what this means is that if I separate capital Q on C1 and C2, then I also separate the same charge Q on the equivalent capacitor. So this right here is also Q over C equivalent. This is a major step, right? And you should make sure that you understand why I could also say that the charge separated on the equivalent capacitance was exactly the same as the charge separated on each capacitor in series, right? But here is my backbone equation. It's the relationship between the potential differences. But what's interesting is if I know the potential difference, then I can say something about capacitance. And because all of the potential differences are in terms of the same charge separated but different capacitances, look at what we can write. So the change in potential, or the difference in potential across the equivalent capacitance, is right here, and it is equal to the sum of the potential differences across the other two capacitors, but those are simply this. And this is where I'm going to write, right? Can you see that the capital Q is a common factor? So it's not relevant to this relationship. What's relevant is this. So you have to be really careful with this formula. I've seen people make the following mistake. They make the mistake of saying that this is true and this is not true, right? This is wrong. They also make them, so I'll leave it at that. You can actually, if you wanted to, you could get common denominators. So you could write, for example, so this absolutely is a mistake. Let me put that in a box. But the following thing is not a mistake. This right here is what is kind of the answer to this exploration currently. So, but you can do some algebra and you can rewrite this if you use common denominators. So on this term right here, what I would do is multiply top and bottom by C2 over C2, right? And on this one, multiply by C1 over C1. If you multiply by C2 over C2, this is multiplying by 1, which you can always do and not actually change your expression. And over here, multiplying by 1 also doesn't change the expression. So, but what you get is common denominators. It's C1 times C2 and C1 times C2 on the denominator. So this looks like 1 over C equivalent equals, right, C2 times 1 is C2 over C1 times C2. But I hope you can follow this. It'll be C2 plus C1. All divided by the common denominator, which is the factor of C1 and C2. And what this means is you can flip this over, right? And C equivalent equals the product of C1 and C2 divided by C1 plus C2. If you have a situation where you have a lot of capacitors purely in series, right? So let's say C1, C2, C3, up to Cn, then 1 over the equivalent capacitance, which is the total capacitance of this series-only combination, is just the sum from n equals 1 up to, actually, sorry, I'm kind of overusing symbols. So let's use the index I, and we're doing the indexed summation from 1 to n, right? But you're adding the inverses of the capacitances. Oops. Right? So this is also a basic result. And it just goes, it's actually the very same process. You imagine, right, the exploration starts with going ahead and separating charge Q. So Q minus Q, Q minus Q, Q minus Q, all the way to this. And the sum of the potential differences across each of the capacitors separately is the total potential difference across the equivalent capacitance. And you will end up just getting this expression. And if you wanted, you could go through the motions and determine that the equivalent capacitance is the product C1, C2, C3, Cn. So it's the product of all these capacitances divided by the sum of all the capacitances. And this is just a common denominator thing. Yeah. So here are some results you can use. These can only be used for purely series combos. That is, there's nothing parallel in between C1 up to Cn. That is, between C1 up to Cn is purely in series. And then you can use these rules. If it's not purely in series, you have to be more clever. So let's do the parallel combo next. The parallel combo is similar. You use the same rules, but it actually feels quite different. So let me show you that this time we're only dealing with two separate conductors. Remember that argument from the previous video. I've got the upper conductor and the lower conductor. And more than that, when I explore separating the charge, there's no reason that the charge separated on the left-hand side has to be the same as the charge separated on the right-hand side. So here's how you understand the equivalent capacitance. We say that this upper conductor has the charge Q1 plus Q2. And the lower conductor has the charge negative Q1 minus Q2. So that the net charge separated is Q1 plus Q2, right? So another thing is whatever the potential difference is across capacitor number 1, it's equal to the potential value of the upper conductor minus the potential value of the lower conductor, but the lower conductor and the upper conductor, it's the same potential difference over the capacitor C2. But remember the basic relationship. So C is Q per delta V, which means that if I solve for the potential, I'm sorry, I always have to do this. I can never just remember it. It's Q per C. So that means, right, so since the potential differences are the same over the two capacitors, that means that whatever charge is separated across capacitor number 1 divided by the capacitance of capacitor number 1 must be equal to whatever charge is separated over capacitor number 2 divided by the capacitance of capacitor number 2, right? So this is interesting, and this is interesting. The net capacitance, or the equivalent capacitance, is going to be, right, the net charge separated over the pair of capacitances divided by the potential difference across the equivalent capacitance. And the upper thing is just Q1 plus Q2. The bottom thing is the potential difference across the equivalent capacitance, but this is actually all common, right? So the potential difference from conductor number 1, which is the top piece of metal, and conductor number 2, which is the bottom piece of metal, that's all the same, right? So this is just delta V, right? So we have this line of equations. And so delta V is a common denominator on Q1 plus Q2. So this is Q1 over delta V plus Q2 over delta V. But Q1 over delta V is C1, and Q2 over delta V, right? So delta V is also the same. I already wrote it. Delta V is also the value of delta V2, right? That's just Q2 over delta V2, which is C2. And the idea is in parallel, you just add up the capacitances. But let me caution you again. Purely parallel combinations are easiest. You just add them together. But if you have mixed situations, it's not so easy. So let's just really quickly, I'm going to indicate to you how you would solve a mixed combination. So here is a mixed combo that I actually drew in the previous video. C1, C2, C3, and the question is, between these two circled points, what is the equivalent capacitance? And the way you would do this is you would take a sub-step. What is the equivalent capacitance for C1 and C2? So let's call that the equivalent capacitance for just 1 and 2 together. They're in series, so 1, or actually let's use the sort of technology I gave you. This says that the equivalent capacitance between 1 and 2, which is purely in series, right? If you imagine starting here and going to there, C1 to C2 is purely in series. It's just C1 times C2 divided by C1 plus C2. And now you can get the equivalent capacitance of 1, 2, and 3, which is the parallel combination of C3 and the series of C1 and C2, which is just C3 plus C equivalent 1 and 2, right? We're imagining this being rewritten as a single equivalent capacitance, 1 and 2, and this is just that, right? So if you're given the capacitances of each of these things, you would just write this answer down. But you're kind of doing some of you this may resonate with. You're kind of doing a recursive process. So you do a recursion. You kind of like go into your big capacitor network, and you just look for the simplest pure combinations of purely series and purely in parallel, and you go all the way down until you go down to those pure combinations, and then you start coming back up, converting pure combinations into sub-steps of equivalent capacitances, and you recurse all the way out to the end, which is a single equivalent capacitance. All right.